We'll let Timur introduce Nick, and we can go ahead and begin the first presentation.
All right, so tonight we have Nick, and you're going to see him again at ADC, but tonight he has a different talk for us. So Nick Thompson is actually an independent audio dev contractor, and he has an audio plugin company called Creative Intent. And he also has another project called Elementary Audio, which is the one that you're going to be talking about tonight, and specifically going to be talking about how to build a plugin with Elementary Audio. So I'm really excited about hearing more about that. Nick, over to you.
Cool. Yeah, first of all, thank you to Josh. Thank you to Timur. Really excited to be here. I love watching these meetups when I get a chance. An honor to be on one. So I'm going to go ahead and share my screen here, which should be a bunch of trees. And you should now see title slide.
You're all good.
All right, cool. So yes, this talk is originally titled Building Audio Plugins with Elementary. I've kind of renamed it Elementary by Example, and I'll explain particularly why in just a second. But as Timur mentioned, my name is Nick Thompson. I'm an independent audio software dev, contracting and consulting. I am one half of Creative Intent, making audio plugins. I have a project that maybe you've heard about called React Juice, and another project that I'm working on nowadays called Elementary Audio. And Elementary will be the focus of today's talk. So for this talk, we're going to look at, first I'll give a really brief introduction to what Elementary is, and then I want to list kind of a couple hard problems that I think we encounter often when writing audio software. And then the remainder of the talk and the majority of the talk will be a series of examples for approaching different aspects of writing audio plugins using Elementary. And for that, I have a series of kind of pre-recorded examples, which kind of get at different pieces of the process that I think is hard and time consuming. And so that's kind of why I renamed the talk Elementary by Example. So yeah, so let's dive in. So Elementary is a new project of mine. It's an audio engine and a JavaScript framework for writing native audio apps. If you are a follower on the Audio Programmer channel, I gave a intro and tutorial series on this project back then, and I would definitely recommend watching through that. And I'll share these slides with Josh and Timur as well so that we can post these links on all the appropriate channels. But in that talk, we kind of go into really the background of Elementary, how it originated, why I think it solves some interesting problems. Today, I don't want to go so much into the details of Elementary other than to say it is really like a functional declarative way of writing both your DSP for native audio apps. And I typically pair it with React.js so that you have this kind of functional declarative approach in JavaScript to building an entire native audio application. On the functional declarative piece, I'm excited to be giving a talk at ADC later this year, and I will really go into why I chose functional and declarative for Elementary. And this is the argument that I'll make is that I think this model is the future of audio. It's one that I'm really excited about and I think have really learned a lot from. So, okay, so I'm not going to go super into why functional. I'm not going to go super into like the background of Elementary. Hopefully I can show you what it is by example. So today we're really just going to look at practical examples. We're going to build kind of a series of quick audio plugins through the examples. And I want to note here too that Elementary itself is a native audio engine and a JavaScript framework that kind of go hand in hand. And it's not just for writing audio plugins. You could write desktop apps. You could write, you could take this to embedded hardware. You could take this to a web audio app in the browser. It's a pretty flexible project. But today we're looking just at audio plugins. Writing audio plugins is difficult. I think writing audio software is difficult in general, but I spend a lot of time focused on audio plugins themselves. Those are the projects I like to work on. That's the space that I like to explore. And in my experience, both personally and from talking to other devs in the space, I think that when we build audio plugins, kind of like with the modern approach, the modern tool chain, we hit a lot of problems over and over again. Oftentimes, I think people will say that the hardest problem in building an audio plugin is building the user interface. But I think it's a bit of a broad term. I think the reason that people answer that question, and the reason I might answer that question the same way, is integrates a lot of different like sub problems. So for example, writing a user interface using an imperative object-oriented model is kind of harder to reason about when you're trying to think about what your application will look like once you've hit save and pushed compile. I think it limits our ability to compose components, and it kind of like involves the problem in C++ at least of ownership and lifetimes, you know, which component should own which component, how do I make sure this one outlasts this one, etc. I also think that iteration time really shows up when under this kind of like blanket of building user interfaces is hard. And for me, at least, that's because, you know, I write my code in C++ with Xcode or something, I hit build, and then I pop up my plugin again. And the feedback cycle there, I think, is really slow. Just right there, that's kind of costly in terms of time. And especially if you're working with a design team and design changes come down the pipe, you know, being able to adapt to design requests is a good, it's helpful to be able to do that with ease. And I don't particularly feel like with the current feedback cycle, I am particularly flexible in that way. And then for me, the big ticket item really, I think, is state management. So a lot of times, if you get into a conversation about why user interface development is hard in audio software, it has to do with state sharing. How do we get information about, you know, the DSP chain to the user interface, and how do we get information from the user interface to the DSP chain? And, you know, this involves multi-threading. This involves, again, kind of like ownership and lifetimes, right? Like, I think it's a common practice to keep your state on the audio processor and then kind of marshal changes over to the user interface at the appropriate time. But as soon as you have multi-threading, you have to deal with synchronization. You have to deal with not interfering with the real-time's ability to be the real-time thread's ability to be deterministic. And so now you're not just dealing with, you know, getting state from point A to point B, but you've kind of coupled all of these other problems with it. This set of problems is the one that I'm interested in really focusing on through this series of examples that I have. And so we're going to kick off with the first example here. And basically what we're going to see is, you know, working with the user interface in code and watching the interface, sort of like how the workflow in this model, what the workflow looks like, really. And hopefully, as we go through this example and the following example, you'll develop an understanding of what elementary itself is. And I'll stop to kind of highlight what's what as we go through here. But so keep these problems in mind as we go through the series of examples. So in this first example, I want to show what it looks like to work with a user interface in elementary. And in particular, I want to use this example to speak to some problems that I've witnessed and heard from developers in this space about how it's hard to iterate on user interfaces the way that we do this conventionally. It takes time. The edit, compile, run feedback loop is too slow. And I think we can fix that. So here in elementary, we're going to start with a really basic example. I have some React.js code on the left. I have in another tab here a development server running, which will relay my code changes into the plugin. And we're using React.js in this example, but you don't have to use React. That just happens to be my preference. You can use whatever framework you like in here. But we've got our code. And then if I toggle over in the background, I have Ableton Live running. You can see our plugin is up and running. This is the user interface that we were just looking at the code for. And so to demonstrate the workflow, let's just start making some quick changes here. Let's say that we get a copy edit from our designer and we make the code change here, we save the file, and we flip over to elementary running inside of live. And you can see that the user interface has updated immediately without, you know, rerunning live, reinstantiating the plugin, anything like that. And let's say that, you know, we have to iterate, we're getting design changes. We want to double down on this statement. But now we're told that we have to These should really horizontally stack, not vertically stack. Whoops. So I'll put them in an enclosing container. I will set the container to stack horizontally. And our changes are right here. Now, this is great, but let's get a little bit more detailed. So you can see down here, we have an input slider that goes from 0 to 1. The value is described by the value defined on line 5, and the input function is, the input handler is defined on line 6. And so when we're working in here, we can drag this slider and our number changes. But I want to show here basically how this workflow extends into debugging and crashing essentially. So let's say, for example, that we want to extend our input slider here so that after we set our slider value, I'm going to try to call this non-existent function. So I'm going to hit save. And now when we toggle back to live, you can see that our preprocessor has already caught this idea that we're going to use this, function named func that is not defined. And so our preprocessor has alerted us inside of Ableton Live without crashing the plugin, without crashing live, that we're about to do something wrong. Okay, let's fix that. I can get around this warning if I try to look this up at runtime. So now when we get an input from the slider, we'll set the slider value, but then we'll try to call this function that we actually can't find on the window object. So this should get me a runtime error. So we see right here, I invoked, the slider input callback. We set our slider value, and then we looked up this function object on window and tried to call it, but we can see that window func is actually not a function. Yes, okay, good catch. So here, Ableton Live is fine. The plugin is fine. We've made a mistake, and we can recover from it without even, without even really thinking, right? I update my code and we're right back here. We're all happy in Ableton Live. Now let's say that I'm confused about what input is coming in here and I want to stop my debugger on it. So I'll update my code with a debugger line. Our code changes have taken place over here. And now I'm going to open up Safari, and I'll close this and I'll show you how I got here. So you hit the develop menu, you can open up Safari. My computer struggles with screen recording software. Now we have Safari opening, the debugger's attached, right? And so now when I change the slider, we're frozen right away automatically at the debugger statement inside of Safari. And I can look in here, oh yeah, okay, this makes sense, this makes sense. Figure out what I need to figure out. And when I'm happy, just like you're used to, right? This is kind of standard debugging, except that I'm doing it in real time instead of Ableton Live. So let's say that I found out what I needed to find out. That's all neat. I can drop my debugger statement. I can hit save. Ableton Live is going to update. And after it updates, I can drag this back. The debugger statement is gone. So that's a brief look, but early takeaways are we have this hot reloading workflow. Your changes update immediately inside of Live. You're protected from crashes. You can attach and detach the debugger at a whim. And ultimately, you can move quickly to develop your user interfaces this way. So that right there is just kind of the first step of building an audio plugin using Elementary. And those takeaways we have there, real-time updating, you have the comforts and the tooling of the modern web ecosystem, crash protection, debugging. But I should caveat here that we haven't actually necessarily looked at Elementary yet. Elementary is really focused on the DSP. And so that is what our next video will be. In a sense, hot reloading within the DAW, this is something we've had already. In fact, like my other project, React Juice, is able to do this just the same. But I think this workflow is worth starting with because the feedback cycle and the ability to describe how your user interface should look and then toggle back to Ableton Live and see it update right away, that I think it's just a different development pace. The speed with which you can implement a design, I think, is remarkable there. But let's step into the second example here. And this time we'll really focus on elementary. We'll focus on what this process looks like when we're ready to start writing the DSP for our plugin. Okay, so in this second example, I want to show something very similar to the first example, which is workflow and what it looks like to work in elementary when you're writing an audio plugin. But in this example, I specifically want to focus on what it's like to write DSP. And so again, we'll start with example code on the left, and you can see I have kind of redacted the example a little bit, or simplified the example rather. We have, maybe 5 lines of UI code at the bottom of this function and 5 lines of DSP code at the top. And I will skip over explaining React really because, there's plenty of great documentation online, but I'll say briefly that this use effect callback that I'm writing here will invoke my core.render call after the component has mounted itself to the screen. You can see here, starting on line 11 with core.render, now we're really dealing with elementary's DSP, and I'm just invoking core.render with the el.in left channel and the right channel. Over here in Ableton Live, we have our plugin running, and this time I have a white noise operator pushing through elementary into an EQ8. And the EQ8 is not really doing anything. It just has a nice spectrum that I like to be able to watch as I'm working on this example. So if I trigger some white noise, we have some white noise. Now, to work with elementary and the DSP, this workflow is really pretty much identical to what I just showed in the prior example. So for example, let's say that we want to write a low pass over the input. So I'm just going to write el.lowpass with a cutoff of 800, a Q of 1.414, and I'm running kind of the same operation on the left as I am on the right. I'll hit save. I'll toggle back to Ableton Live, and this time when I push a key, you can see that by the time we got there, elementary has already hot reloaded and applied the DSP changes inside of the plugin. And I'll show this, kind of in real time as well, because I think this is a pretty engaging example. I'm going to just have Ableton Live play a white noise note held continuously. And I'm going to loop this and hit start. Now, if we watch the spectrum over here, we can see we have our roll off starting about 800. And if I toggle back to the code now, let's say, for example, that I actually want this to be a high pass on both the left and the right channel. So I edit my code, I hit save. And so you can see that, in real time, while the DSP process is running, I'm hot reloading DSP into the plugin. Now, for one, I think this workflow is just really exciting. I mean, I have really enjoyed working in it myself. But for two, I want to explain a little bit or go more in detail on this approach to writing audio processes. And so I want to go through this bit of code that I've saved down at the bottom of the file here to build our example into something more interesting. So now when we're going to go ahead and render, I'm going to uncomment this, tidy up a bit. Okay, so now I'm going to walk through briefly what we have here. What I want to do is build a 3-band EQ. And so I'm starting with this really basic description of kind of the state of the EQ, right? We have our first filter will have state, which involves a cutoff at 800 hertz, a Q at 4.414, and a negative 36 dB cut. The second filter will have the same thing, but at a cutoff of 200, and the third at a cutoff of 1200. Now I'm going to define an EQ function, and the syntax might be a little bit tricky here if you're new to JavaScript, but essentially we're defining this variable EQ, which is a function which takes a single input variable, and the result is the result of reducing our EQ filters over that input. And this is very much like a functional left fold kind of thing. So if I were to kind of write out what's going to happen, we'll get el.peak of 1200, 4.414 of el.peak 200, 4.414, etc. Oh, I forgot the gain, but you get the idea here, right? And eventually inside of here will be the input that we passed in. So this is really just a quick left fold way of kind of accumulating a series representation of the filters that we've defined up top. Now I can change our render statement. So now we're just going to render our EQ over the left channel and the right channel. I'll hit save. I'll toggle back to live. And now when I play a note, you can see we've got our pretty aggressive cuts, right? And let's go ahead, just for example, let's change this one to a 12 dB boost, and we'll turn these off essentially. So I'll hit save, I'll toggle back, I'll play a note, right? And we've got our peak right at 800 there, and the other notches have, well, the other cuts have disappeared. So that's really what I wanted to show in this example. Here we have kind of a 3-band EQ in just a couple of lines of code, and we were able to do it entirely in this real-time interactive workflow inside of Ableton Live, processing real-time inputs. And just like I was trying to speak to in the prior example, I think that the edit run feedback loop here is really compelling. And we will, dig into this a little bit further in the next examples as well. So that example, I think, is maybe the best way I could have described elementary without describing elementary. That is what it's like to work with DSP inside of elementary. And it's this very, functional declarative way of building up your DSP process and then asking elementary to kind of just make it happen. And so what we saw in that video was that the audio engine piece, elementary itself, is able to receive those updates in real time inside the DAW. So now we're not just dealing with hot UI reloading with crash protection and debugging inside of Ableton Live. We're dealing with hot reloading everything that we need to reload to build an audio plugin. And elementary is able to do this with smooth transitions from state to state. In that brief part of the demo where we have the continuous white noise loop, and maybe white noise is the wrong signal to show this on, but when elementary is changing from the low pass to the high pass, it's going to do it with a smooth linear gain fade. There will be no click. And that's because the engine is designed for this dynamic behavior. It's designed to very efficiently go from one state to another smoothly, such that you, the end user who wants to describe what your DSP process should look like, don't even have to worry about how that will be, how elementary is going to do it. It'll just do it for you. So now with these two examples, I think that we have a pretty compelling workflow in terms of being able to write code and see your changes happen in real time inside the DAW, right? And we've eliminated some problems here like lifetime ownership. We have really flexible composition, but we haven't yet tackled this kind of notoriously hard problem of state sharing. How do I share information between my DSP and my UI? And so that's what this next example is really designed to show. So let's jump into that. In this third example, I want to take a small step from example 2, integrate some of what we saw in example 1 to show what it's like to manage state in an audio plugin like this using elementary. So I think this topic is where this conversation gets really interesting. So far we have looked at hot reloading, crash protection, debugging. We've looked at real-time interactive DSP with a functional declarative expression of a 3-band EQ, but we haven't really dealt with user interface state meets DSP state. And this is where I think the way that we do audio software today costs us a lot of time. And it's a difficult problem because it integrates, multi-threading, thread synchronization, lock-free interactions with the real-time thread, who should own the state, how do we communicate state updates from the UI to the DSP and vice versa. And totally, I think it's a very difficult problem the way that we do it today, but I also think that we don't have to deal with those problems every time we do this. And so what I want to show you with elementary is essentially that you don't have to do it that way and that you don't have to fight those problems when you want to work like this. So on the left, we've got our example code. These first few lines should look really similar to example number 2. We just have, a description of our filter state, except this time we're using React hooks. And again, I'll kind of skip over how hooks work, but the EQ filters variable here will take our initial state as described in the following lines, and then we get this set EQ filters function, which allows us to update this state. Now, I've also added a key property onto each of our, filter state objects. And that's just kind of a detail about elementary for handling subsequent, successive calls to core.render. And there's a good article on the elementary documentation if you want to go into detail about really why they're necessary. But in this case, we have an example where they're necessary, and I just put them in. And I will kind of skip over that piece for brevity, really. But so I've updated our EQ function. It looks really similar here. The only difference is that this time when we're constructing the peak filter at each stage, our cutoff and our gain take the form of this keyed el.const node instead of passing, the primitive number types directly. And this, again, just helps elementary get from, state A to state B without you really needing to do much. Now, underneath this, we have a set cutoff helper, and this is really just an abstraction over the set EQ filters that we have above. So when we're going to call set cutoff in response to a slider change below, and what we'll do first is copy the filter state that we have above, and then we'll update the ith filter with a new cutoff value and call set EQ filters with the new representation of our filter state. Then we have the same thing underneath for updating the gain values. We have our core.render step in the use effect hook, which is just running our EQ over the left and the right channel. And then we have our user interface description. And so the interesting thing here that I've added underneath our, description of this example in this UI layout, I've added just a label for the slider. I've added a slider. This one, you can see the value it takes is the value of the first EQ filter, the cutoff, and then when you drag the slider, we're going to call set cutoff for that first filter, and then we're going to give a readout of that filter's cutoff frequency. So toggling over into live, you can see that's exactly what we've got here. And the filter state that we're starting with looks just like example number 2. So it has these kind of aggressive 36 dB cuts. And if I play a note, and there we go. So we can see that as I'm dragging the slider, right? I'm calling set cutoff. Set cutoff is this quick helper on top of set EQ filters. Set EQ filters updates our filters, filter object right here. And then we call our use effect hook again. The use effect hook calls this EQ function again, and we propagate all of our new cutoff values into the DSP through elementary. And now I want to take this a little bit further too. So I'm going to grab some code that I have at the bottom. This is a practice I like to do to keep these screencasts a little bit shorter. I'm going to uncomment it, and I'm going to remove the interface piece that I had added. Okay, so now what I'm doing here at the bottom is in kind of our slider box, I'm starting with the EQ filters. Again, this is just our list of objects representing the filter states. And I'm going to map over them such that for each EQ filter in that list, I'm going to return a chunk of user interface, right? And each chunk of user interface is going to have a label, a slider for the cutoff, and you can see that's right here. It will take the cutoff value for the appropriate filter. It will assign a on input callback for updating the appropriate filter. Then it has a readout and then a slider to do the same thing for the gain and a readout for the gain. So when I hit save here, I can toggle back to live. We can see the hot reload take place. And now we can play with our filters. Cool, little white noise drone action. So this example, I think, is really starting to get interesting because you can see that I'm using the exact same EQ filters data structure to build my user interface to represent values of the sliders. And I'm using the exact same, state update callbacks from the sliders to update the state that describes the DSP, right? I mean, each time the state changes, we're going to call core.render. We're going to invoke our EQ function. Our EQ function is going to, coming back up here, reduce over the new state of the EQ filters to apply a new cutoff value or a new gain value onto our series description of the 3 biquads. And so there's not even a thought about, does the processor own this? Does the UI own this? How do I get this from the UI onto the processor? Is it atomic? Do I have to use a lock-free queue, etc.? You just don't even have to engage those problems when working this way. So I think that's a really compelling workflow again. And in the next, I'm going to stop that one right there and keep moving here because I realize I'm going to run right up against my time. But so the point that I wanted to show in that video is that it's the same state that describes your UI and your DSP. And it's not just, you could say that maybe for a traditional C++ audio plugin, right? But what I mean about this is that, like, mentally, it's the same thing. You write a single kind of data structure, and the data structure is simply an input to this function that describes both your UI and your DSP. And you don't have to worry about anything else. You don't have to figure out how to get that from thread A to thread B. You don't have to figure out, how to make sure that you are in sync with the audio thread, lock-free queues, all of that stuff. You don't even have to pay attention to it. You can just focus as you're working this way on what your app should be. Now, that example really shows kind of like state as an input to the description of the function which describes your DSP and the function which describes your UI. But the last thing that I want to show is the other way around, right? Like, we also have situations where what's happening in our DSP chain very much informs the state of our user interface. And so for this, kind of the classic tutorial that, at least that I've witnessed, is drawing a gain meter. So I want to kick that off. This will be the last example, and then we'll wrap up. So in the last example, we looked at how we can use the same state to describe our DSP chain and describe our user interface, and how manipulating that state does not need to be such a complicated process of coordination from the processor to the UI and vice versa. But in that example, we only really demonstrated new state values flowing from the user interface really over to the DSP. Take information from the DSP back into flow direction. So starting again with our code, We have example 04. We have these two React refs. I'm going to try to skip over explaining how React works. I would encourage you to read the documentation if you're really curious on it, but you'll see where we're using them below. And then I have this meter values struct. So this will be the value that we can pull out of the DSP chain for both the left and the right channel. Then we have our use effect hook, just like we've seen before. Again, I'm rendering here a very simple pass through, left channel goes to left channel, right channel goes to right. Now here things get a little bit interesting. After we've rendered our DSP, I'm going to grab my canvas ref, which is a way of just getting a handle on an underlying piece of the user interface. And from that canvas, I'm going to create a drawing context. Now I'm going to use my other ref to basically ask the user interface to redraw me on the next animation frame. So this is basically like signing up for a 60 FPS draw function or something like that. So when that happens, when the next frame is ready, I'm going to draw my meters using the context we just grabbed, a width of 200, a height of 50, and the meter values that we have defined on line 36. And then I'm just going to ask for the next frame. So, keep this 60 FPS drawing thing going. And then down here, again, this is just some React, but basically when this component is trying to leave the screen, I want to make sure that I stop asking to be drawn. So very simple. Now I want to show this draw meter function. Actually, before we get to draw meter, let me come down here to the user interface that we render. So like the other examples, we have just a big container with a logo. We have a description of this example. And now here I have a canvas. And the canvas, you can see I'm passing the ref here. This is how I'm able to grab a handle on it later with a width of 200, a height of 50. And if I toggle over to live, you can see this is what we've got, right? Logo, description, and then a nice gray meter box. So now let's come up and take a look at this draw meter function. So up at the top, I have draw meter, and I'm setting a gray fill, filling the whole rectangle. Then I'm creating a gradient for drawing the actual meter values. And now I'm taking the left value, running it from amplitude to decibels, and this is clipped at -96 dB. So I have I'll draw from -96 to 0 in our examples. And then I'm just mapping that here onto a 0 to 1 value so that I can fill a rectangle, representing the left meter value and the right meter value. And over here, obviously we have set those meter values to 0 at the beginning, so we're not drawing anything, and we've connected our inputs to our outputs. So when I play the noise, we hear noise, we don't see anything. And so, for example, if I were to put this at 0.5, 0.7, I can save, I can toggle back, and we can look at what these values would be drawn at on the meter. And we have that cool gradient in there, which looks nice and all. But we're now stuck, right? So we have our user interface description, we have our drawing function for drawing the gain meter. We just need to get values out of the DSP. So to do that, what I'm going to do is insert into our DSP chain a meter node. So, oops. Hey. Okay, so I'm going to meter the left channel, and the meter node will actually also just pass through its input. So I still have a pass-through chain here, but now I have this neat benefit basically of being able to say, when I get meter data for the left channel, which comes through as a through the elementary core event emitter, I'll get a new value, and I can say meter values.left equals V. Now, I don't really have to do much else here because just down here, I have this, 60 FPS draw loop. And each time I'm drawing, I'm going to ask for, I'm going to read this meter value. So, at some point in time, I'll receive this event, I'll write my meter value. At some time thereafter, I'm going to have another draw frame invoke, and I'll read the value and draw the updated state. And then down here, I just have to make sure, just cleaning up. Oops. I'm going to let go of that listener when we're trying to update. And if I save now, I should be able to toggle back over to live. You can see the left channel value was written to 0. And so if I play noise, there we go. So we've got the left channel updating already, for what was that? Like 2 extra lines of code. Let's do the same thing for the right channel. Key right channel. And this key here, I mentioned it in the last video, Elementary uses these keys to distinguish different nodes in the chain. But in this case, it also uses it to label the event name that's coming out. So I've got the left channel, the right channel. I will update the right channel accordingly. I will remove my right channel listeners when it's time to go, hit save, toggle back over. We've updated. Great. So just like that, we have information flow from the DSP back to the user interface. And again, we don't have to deal with lock-free programming, multi-threading, none of it, right? You just write JavaScript. And for those of you who have worked in JavaScript apps before, this should feel pretty familiar, right? You just deal with the JavaScript and leave the rest be. So I want to grab this guy for a little extra, and I'm going to put him here. Okay, so now I can, right? And you can see the left and the right channel in the gain meter reacting accordingly to the auto pan. Now, this is cool. I mean, already I think this is really exciting, but I think we can do something else a little bit more interesting still. So I'm going to zip down to the bottom and grab some code that I've written like I usually do. And I'm going to pop it in here. Oops. Okay, now I'm going to delete our previous render statement. Okay, so what we're doing here now is into the left channel, we're going to add the result of muting, just multiplying by 0. It's muting the meter channel. And so we're going to meter the left channel, but first we're going to use an envelope follower. And this is so that we get kind of, that nice quick attack and slow release that you're used to when you watch a gain meter. And we're going to run that over the left channel, but we don't want to propagate that signal. So I'm muting it, and then I'm summing in the actual left channel. So this will just be a pass through of the left channel, but I have my meter running on the envelope. Same thing here, doing the same exact thing for the right channel, and attack and release are just, we're using this tau2pol function from the elementary library to define a 8 millisecond attack and a 50 millisecond release. So here, when I hit save, I can toggle back to live. And after the update, you can see how much smoother that drawing is, right? And I could put a quick decay on this. And you can watch, just like the meters that you're used to seeing, we have kind of that quick attack and that kind of slower fall off, but I still get the pan updates. So that's it. I mean, that is one of the ways that you can take information from the DSP processor and use it in your user interface. I'm going to cut that one there because I realize I'm coming up on time. But with that example, I really wanted to show that, in example 3, basically, we had state moving towards DSP. In example 4, we have state moving from DSP towards UI. And in both cases, I think it can be free of the problems of multi-threading, synchronization, state sharing, et cetera. We can, I think basically through elementary, we have a way to build audio software, the audio software that we want to build with kind of like a much simpler mental model of how we need to write this code. So after all of that, after all those examples, the few takeaways that I really want to leave you with are that I think writing audio software is hard. We set out to build products in this space, audio plugins, desktop apps, embedded hardware, et cetera. And time again, we kind of like involve ourselves in a suite of software programming problems that I'm not sure we have to. And so these are hard problems, and hard takes time, and time takes money. And I think that we should look for tools that let us focus on the problems that really matter, the what, not the how, right? Like we have these ideas of products that we want to make, what the interface should look like, how they should sound. And that's very much the what of our product. And I think that we can establish tools that take care of the how for us. And the result, if we succeed there, I think we have a better development experience. I think it'll be faster, save you time, and save you money. Thank you. Really excited to be able to give this talk. Check out Elementary. There's a website there. The second link is a link to my personal blog where I'm writing blogs about it. The third link is the Elementary Audio Discord community. And then the fourth link is the Audio Programmer Discord. I'm in both of those. I'm at Nick. Please reach out to me if you have some questions or you want to give it a try. You can use this today at your command line and kind of explore the engine that way. And if you're interested in making audio plugins this way, hit me up. Let's talk. Thanks.
Thank you very much, Nick. That was really fascinating. I have so many questions now about this.
Great.
I don't even know where to start, but I guess all of these questions like can be summarized with like, how does it work? Because obviously, I think maybe I'm missing something, but all of these problems of like multi-threading and synchronization, all of the stuff, you have to solve this somewhere, right? So, and I'm assuming that is all just kind of magically solved in the backend, which is running all of this. And
yeah.
So I'm just really curious if you can share any detail about like how that actually works and what is this JavaScript stuff that we saw, like what does that run on basically? How does that work?
Yeah, of course. So Elementary itself kind of has two pieces. One of them is the native audio rendering stack. And then the other one is this JavaScript library, which is what you just saw so much of. And I'll stop my screen share here so you can see my face. So yeah, right, two pieces. There's the native audio rendering engine, and then there's the JavaScript library. And the JavaScript library is really what you see. It's what you work with. And when you ask Elementary to render something for you, so you can describe your audio process, you give it to Elementary. What Elementary will do is essentially look at what you have already rendered, look at this new thing that you're trying to render, and then figure out basically how to direct the underlying audio engine to get from state A to state B in the minimum possible set of changes. And then the audio engine is designed basically to receive, change sets at any time in a totally like deterministic, memory allocation free, et cetera, channel, and apply those updates on the audio processing thread. So yeah, you're totally right? Like these problems have to be solved somewhere. I think that if I do what I'm trying to do right with Elementary, then you don't have to think about it. They're solved for you.
That's really cool. Thanks.
Does that answer your question, Timur?
So I guess you chose JavaScript because obviously there's a lot of tools for JavaScript. There are lots of people who already know JavaScript. How do you solve the problem that you can't really run JavaScript in a kind of real-time context because there's a garbage collector?
Yeah, so the JavaScript engine in this case runs on the main thread and communicates like we have the real-time thread running there, but pretty much everything that you do when working with Elementary will run on the main thread. And we're perfectly happy to run a garbage collector there, and it won't interfere with, rendering audio on time.
Okay, one last question about this, if I may. How do you then do stuff that needs to be sample accurate?
Yeah, cool. So when you're describing an audio process using Elementary, you are basically describing a graph topology, right? And so when you send a set of changes from the core interface down into the audio engine, the audio streams that all render thereafter are all sample accurate. So as long as what you wire up kind of like delegates to the engine, you'll get sample accuracy, which is to say, for example, you can pre-compute your biquad coefficients if you'd like to by doing it in JavaScript and then kind of avoiding asking the elementary engine to compute them via the real-time thread. You could also ask, you could send kind of the math operations over to the elementary engine and have your biquad coefficients run per sample if you want to, up to you. And kind of from that point, basically everything is sample accurate. Now there's some, in terms of, for example, Midi handling. Midi handling is,
exactly, yeah. Like if you want to build a sequence of the stuff, for example, or something like that, right? Yeah,
so I actually have an example already in the examples repository that I have on GitHub. You can also build a sequencer with like sample accurate kind of pulse trains triggering a sample playback engine. But again, like to take MIDI information and hit perfect sample accuracy with MIDI, this gets tricky, right? Because now if I want sample accuracy within my audio buffer, I don't have time to essentially like put a message over on the non-real-time thread, invoke JavaScript, take the answers and get it back, right?
That's exactly it, yeah.
Yeah, so in that case, like when you use MIDI with like using the JavaScript interface, you kind of forfeit that level of sample accuracy. And this is kind of like the pro tier, if you will. Like elementary has a embedded SDK, and you can take the runtime engine embedded in your projects and deal with like sample accurate MIDI however you need to. But I think this is for essentially, I think there's a subset of applications that we're trying to build that are willing to give up a millisecond or two of latency on their MIDI accuracy, and certainly plugins that don't even use MIDI. But yeah, it's kind of like if you defer it to JavaScript, you accept a little bit of guesswork. If you strictly cannot do that, you could take the elementary SDK and kind of get in there by hand.
That's pretty cool. So what's the deal here? Is this some open source, closed source? Is this something that you're going to like productize at some point, or is this just some like a kind of playground kind of thing? Like what's the idea here? At what stage are you at with this? What can we do with this today? Like this is kind of really curious about that, because it sounds like it's a really interesting toolbox to kind of just go and build stuff with this, right? So how far are we away from actually being able to build stuff with this, and what do we need to do for that?
Yes, totally. The plan basically is you can use the command line tool today. So if you go to the website, there's a documentation page and you can install the elementary command line tool. You can write JavaScript, run it, hear your audio. That's all available for free today. I'm aiming at a licensing model that basically says like, use this for free for your personal projects however you want. And at the point in time that you intend to commercialize it, let's talk about a commercial license. And that's kind of the same approach that I'm preparing for with the audio plugin developer kit. So in the next few weeks, basically, I'll be onboarding some early kind of beta users to use this plugin kit. And once you've written some JavaScript that describes your app and does your DSP and stuff, essentially I have a tool chain for just printing like a, pre-building a VST that just takes all of this up, and you could go and put it on your web store and sell it to potential customers and whatnot. And that kind of process for going from development to commercialization will be a commercial license type of situation.
Cool, thanks. Well, that's really interesting. Could you maybe repeat again where we could find information about this? What's the website? Is there a website? Is there GitHub? Is there something else?
Yeah, of course. It's elementary.audio.
Right. Yeah, you had that on your slide, but like maybe it would be good to also put that URL later in the comment on the video or somewhere else where people can find it.
I'll do that right now.
Cool. Well, thank you so much. I'm sure there are lots of questions also on the YouTube chat, aren't there, Josh?
Loads, yes. So thank you very much, Nick, for that really awesome presentation. And first question is from Mark Donardo, who asks, will there be a repo of these examples?
Sure. Yeah, happy to.
Okay. And that would be on the elementary audio GitHub?
I will put it, actually, I had started working on this in a separate repo. So I'll make a new GitHub repository just for these examples. It'll be /Nick Thompson /TAP meetup examples, something like that.
Great. Just send me that example, send me that link when you get a chance, and I'll put it in the description in the video.
Yep,
okay, great. Shellac85 asks, can this be extended with things like Redux and Material UI?
Yeah, totally. In fact, the examples that I have here are using Tailwind UI for kind of like handling the style components. The very first example that I showed in terms of like just doing user interface in a plugin, that piece is actually pretty simple. That's just a web view running in a component, right? And like, there's been a few companies who've explored this already. You could do that today without elementary. That's totally, I think, a worthy exploration. And with that, you can do Material UI, Angular, Vue, Svelte, whatever you like. I think in this case, things get really interesting when you can do your UI work that way and then also do your DSP work right there as well.
Great. At Sushi asks, is the entire runtime specifically for desktop, or would it run on iOS and Android as well?
Yeah, it can run pretty much anywhere. The core piece is all just like my own homegrown like C++11 library. So standard library stuff, you can take it wherever you can compile the standard library.
Great. And another question from at Sushi, who asks, UI support wise, is there any difference between React Juice and elementary?
Well, yeah, good question. I mean, you could use elementary and React Juice together as well. So React Juice is basically like running React code in a JavaScript environment and then assembling Juice components, native Juice components to represent your user interface inside your audio plugin. You could run that JavaScript in the same place that you run your elementary, your elementary JavaScript, and have kind of React Juice on the back end for your UI and the elementary engine on the back end for your DSP.
Great. And Martin Wood-Mitrowski asks, how are parameters exposed to the host?
Yeah, good question. So in the demonstration that I provided, there's kind of like this idea that I'm working on of a development kit. And ideally, I could just hand out the development kit for free to everybody who's interested in this. And the development kit exposes some like fixed parameters that you get like 8 macro params that the host will see. And then when you drag them, you'll receive, event emitter callbacks on that same core, elementary core interface that you received like the meter readouts on. But for kind of like for the step where you've written your product and you want to take it and sell it as a plugin or something like that, you can actually there's a JSON input that you can list out your parameters and then it'll kind of like build up that way. So you would essentially like write your JavaScript, put a JSON file next to it, and then you're good to go. Great.
And Martin also asks if you could talk briefly about how you can make your own elementary modules, both DSP and metering.
Yeah, so you can write them. I should say there's 2 ways to write modules. One of them is, I think I've done my job well if you can express a huge number of DSP processes just composing over the functions that are already available to you. And so I have an example repository of this too. If you go to my GitHub, I have a drum synth library, and it's a couple like standard drum synthesis sounds that are all made using the built-in feature set. And it's a library that you could npm install and use in your own project right now if you like it. And so that's one way to build kind of your own components, is just by composing over what's there. And then if you need to like really, roll up your sleeves and get into some really specific, sample accurate C++ stuff, or maybe you have some pre-existing proprietary DSP that you can't or don't want to rewrite in JavaScript or anything like that. The SDK is also, you can like extend it with native nodes yourself. So you could kind of write some C++, plug it in, and then from JavaScript, el.mynode and bring it up that way.
Great.
Can I ask another question actually, because it's kind of somewhere around this area, because you just mentioned JavaScript DSP. How would the performance of kind of this JavaScript type DSP compare with DSP that you kind of write by hand in C++? Have you benchmarked this? Do you have any idea of like how performant it is?
Yeah,
I mean, I don't really care about UI performance, but obviously DSP, that's where it gets interesting,
Totally.
Because that affects your CPU load and
totally,
affects you as a music producer or whatever quite directly.
Of course. So I don't have hard benchmarks yet. I'll be doing that in hopefully the next few weeks here. I have some like kind of anecdotal benchmarks so far, which I'm pretty excited about. I should clarify that, Elementary is never running JavaScript on the real-time thread, right? So the performance basically is how fast Elementary's native audio engine compares to what you would have written in C++ by hand. And those are the benchmarks that I'll be releasing. And generally, so far, I've had a few experiences at this where I set out to write something in Elementary. I can't figure out how I'm supposed to do it. And then I start tackling it in C++, thinking that like, oh, I must have to like extend the native library. And I write my thing in C++ and I run it, and it's, X fast. And then I realize, oh wait, I should have just done this like this in Elementary. And I rewrite the same thing in JavaScript using the engine as it is today. And so far, each time, what I've written in JavaScript outperforms what I had written by hand, which is just a funny, it's anecdotal so far. And like, don't take my word on it until I share the benchmarks, which I will do. But it's an interesting thing. I mean, I like to think that I'm a fairly good C++ developer, but, writing extremely high performant code, it's challenging. It's not always like obvious the way to do it. And so essentially, I think that an extremely well optimized engine, which I aim to deliver, would often get you faster than what you were going to write in C++, unless you're like, top of the game C++ performance engineer. And those people are out there. Maybe they shouldn't use what I'm working on. That's fair. But, for me, I think what I'm able to do here is so far exciting in terms of performance and well worth whatever like 1% CPU costs I have, something like that, Anyways, that's kind of rambling. I'll give you real benchmarks ASAP.
Great. Vera Khan asks, and maybe you know what he means by that, or she. How does a JavaScript functional imperative model improve the iteration time? Not sure what they mean. The iteration time of, not sure. Yeah. Any thoughts on that at all?
Yeah, I mean, so I think like the point that I wanted to make in the examples about iteration time is really about being able to like write your code and have it immediately hot reload right next to you, both DSP and UI. And then there's a question, as far as I understand this question, I think there's kind of a step you could go further, which is like, assuming I have that, would I be faster writing imperative, or would I be faster writing functional declarative? And here, I don't know if there exists a concrete way to say X is faster for these reasons. But in my experience, moving to the functional declarative model has made me like wildly faster in terms of what I'm able to do, because I can think just in terms of like, you know, what my UI should look like or what my DSP change should be drawn like, and skip the rest in terms of like the imperative procedure of, you know, add child A to child B, add child B to child C, set child B to like left 500, top 200, et cetera, et cetera. Like my brain can't look at that and paint the picture very quickly. But if I'm looking at, for example, like HTML or React's JSX, I can look at a couple lines of code and get a pretty good idea of, you know, what this is going to look like. So, you know, that question might be a personal preference thing ultimately. But I've really been enjoying working in, you know, functional software.
Okay. Giovanni Casanelli asks, would it be possible to integrate machine learning Python code into the workflow? For example, speech audio is sent from a DAW to elementary to Python, which inverse text is sent back to elementary. Is something like that possible? That sounds like a very specific use case, but
you can do it. Yeah. I mean, I don't know how well it would work out ultimately, but you know, once, like if you go grab the command line tool off the website today, you can, like when you receive kind of those audio callbacks or when you receive those data callbacks on the JavaScript thread, that command line is built on top of Node.js. So you could, for example, connect a socket up to, you know, a UDP server that's hosted locally by Python app, send stuff over the socket, run whatever you need in Python, run it back, you know, over the socket connection, etc. You could try to do something like that. I don't know if it would be great, but I think you could probably try it.
Sounds beyond my pay grade. Okay, so Stefan Letts, Mr. Faust himself, has a couple questions.
Yeah.
So let's see. So could we generate elementary code from Faust DSP? And Stefan clarifies a little bit more. In the Faust compile, we have an intermediate signal-like representation of what could possibly be compiled in elementary. So I guess there's a question of, would you be able to take Faust DSP and convert it into elementary code?
Interesting question. I'll first say, huge fan of Faust. I think that's such a cool language. I've used it a bunch myself. And if I wasn't such like a JavaScript geek, then I might still be using Faust more than I'm using this thing. But yeah, that's an interesting question. I guess I'd have to look at the like kind of intermediate representation. I know for sure there are some things that you can, like in Faust, you can have like a single sample feedback cycle, which is how a lot of kind of like the, you know, the filters are written in the Faust library. So far, I'm kind of like disallowing you from doing that in JavaScript. And so like that piece, I think we'd have to figure out. But I think also like, depending on what kind of the intermediate stages look like, you could maybe take like Faust code that needs a single sample feedback loop and kind of like JIT it to LLVM or something, and then pass that down into kind of like the native side of elementary's audio engine. We'd have to explore. It's an interesting question. I think that'd be really cool.
Sounds like an interesting discussion to have. So Stefan has another question. Are there any delay lines yet in elementary?
Yeah, you bet. Totally. el.delay. It's documented in the, if you go to docs.elementary.audio, you'll see one there. And I'll probably be adding a couple extra options there in the coming months and weeks.
Great. So that's all the questions that we have from the chat. Thank you once again, Nick. And Once again, the site to go to check this out is elementary.audio. And we hope you go and check it out. Really awesome developments happening. And yes, that's it. Thank you very much, Nick.
Thank you.
Thank you, Nick. That was super interesting.
Yeah, thanks. This was super fun.
Yeah, really cool. Great. So I guess it's a good time for us to jump into the next talk.